Given two functions f and g, consider the function obtained by taking the quotient f over g. Let's see how to obtain its derivative by using the derivatives of f and g. We immediately observe that, as for the derivative of the product, which is not the product of the derivatives, the derivative of the quotient is not the quotient of the derivatives. In fact, consider, for example, both f and g equal to x. Then f over g is the constant function equal to 1. The derivative of a constant is 0, while the derivative of x is 1. And therefore, the derivative of f over g is 0, while the quotient between the derivative of f and the derivative of g is equal to 1. Clearly, these are two different functions, so it is not true that the derivative of the quotient is the quotient of the derivatives. The formula that allows us to calculate the derivative of f over g is called the quotient rule, and is contained in this theorem. Let f and g be two differentiable functions at x, and suppose that g of x is not 0. Then the quotient function f over g is also differentiable at x, and its derivative is given by this ratio. The denominator is g squared, while the numerator is f primes times g minus f times g prime. Let's see an example.
Let's compute the derivative of this rational function. The numerator, denoted by f in the quotient rule, is this polynomial 4x plus 2, while the denominator, g, is the polynomial of degree 3. Let's first compute the derivative of f prime, that is the derivative of 4x, which is 4, plus the derivative of constant 2, namely 0. So we have 4. And in the same way, the derivative of g prime, is the derivative of x to the power of 3, that is 3x squared, minus the derivative of the constant function 1, that is 0. So we have 3x squared. Now we are ready to use the quotient rule. So y prime is equal to f prime, that is 4, times g, that is x cubed minus 1, minus f, 4x plus 2, times the derivative of g, 3x squared, divided by g, x cubed minus 1 to the power of 2. Now we compute the products. Now we sum up these two terms. The result is this, which is the derivative y prime of our function.
Why does the quotient rule look in this way? To understand it, we can proceed in this way. Let's call big F the quotient function f over g, and suppose that we already know that in addition to small f and g, also the quotient function is differentiable at a certain x. Obviously, we must assume that the function g is different from 0 in order to calculate the quotient f over g. We can now write f as f over g multiplied by g. Then f prime is equal to the derivative of the product between big F and g. We now calculate the derivative of big F times g with the Leibniz rule. The derivative of the first function, big F prime, times the second, plus the first function, big F, times the derivative of the second, g prime. Thus, we obtain this equality. Let us now isolate the term that contains the derivative of big F. Now, recall that big F explicitly is the ratio f over g, and bring to the common denominator. Finally, we divide by g of x to get the derivative of big F. Remembering that big F is the ratio f over g, we have thus discovered where the quotient rule comes from. We conclude by highlighting the rule for the derivative of the reciprocal of a function as a special case of the quotient rule. In fact, it is sufficient to choose f equal to the constant function 1 in the quotient rule and remember that the derivative of a constant function is 0. The derivative of 1 over g is therefore minus 1 over g squared multiplied by g prime. For example, the derivative of 1 over logarithm of x is minus 1 over the logarithm of x squared times the derivative of logarithm of x, which is equal to 1 over x. The result is therefore minus 1 over x times the square of the logarithm of x.